Hello friends, thank you so much for your time to watch my YouTube channel. Thanks also if you have already subscribed my YouTube channel, and then you may click the bell notification so you'll get the update any videos about mathematics and physics in my channel. In this video, we will discuss about measurement and uncertainties. Why I say discuss? Because I want to share the history of the fundamental international systems of units. And if this video is good for you, and you may share to the others. If you're talking about the history of fundamental units, the universally accepted method of expressing physical measurement for the world, commerce, industry, and science is about units. And then they have already improved the knowledge of the fundamental constant. And that is why in physics, we will get the new 7 base fundamental units. Related to the history of fundamental units, the International System of Units, or we can say SI units, was established in 1960. Its origin goes back to the creation of the metric system during the French Revolution. Following an idea proposed a century earlier by John Wilkins, John Wilkins said the new system of weights and measures took as its starting point a single universal measure, meter, and used it to define length, volume, and mass. To define meters based on John Wilkins' idea, so meters came from a perceived constant of nature, means 1/10,000,000th of the distance along Earth's meridian through Paris from the North Pole to the equator. To define the volume, with the liter being 0.001 meters of distilled water at 4 degrees. To define mass, the kilogram, the mass of 1 liter of distilled water at 4 degrees Celsius. Subsequently, in 1799, two platinum artifact standards for length and mass based on those definitions were deposited in the Archive de la République in Paris. In words of the Marx de Condorcet, a new system of measurement for all time, for all people, was born. It's very interesting, actually, if you want to follow the history of the fundamental units. Continue to the 76 years later, the signing of Meter Convention in 1875 established 3 international organizations, which are the General Conference of Weight and Measure, or we can say CGPM. The second organization is the International Committee for Weight and Measures, or CIPM. And the last is the International Bureau of Weight and Measure, or BIPM. They say that tasked with maintaining the SI and continue to do so. So means They were formally tasked with maintaining the SI and tried to continue to research the fundamental SI units and so on. Because the SI is a living, evolving system, changing as a new knowledge and measure needs arise. And also, sometimes slowly when measured against the rapid pace of scientific progress. In 18th or 19th centuries, the natural philosophers or scientists tried to apply the system of length, mass, and time, with time defined by astronomical observation to quantify newly discovered phenomenon. And there are some scientists to try to apply the system of length, mass, and time. And then that system, that scientist is Gauss, Weber, Maxwell, and Kelvin also. And the system of length and time, mass, with defined by astronomical observation. And then this is to quantify newly discovered the phenomenon, which is magnetism, electricity, and the concept of energy and new units of measure. And the other pioneers also try to expand the system and develop the conceptual framework of coherent system with base mechanical units from which to create it derived unit as needed. And this is the new SI will specify the exact value of 7 fundamental constants. And all SI units will be based on those defining constant, starting from 1668, starting from the John Wilkins essay is published, and continue to 1799 means the metric system is born, and the Archive de la République in Paris received 2 platinum artifacts standard representing the meters and kilograms. And it is developed also in 1875. 17 members nations signed the meter convention. Work begins on constructing a new international prototypes for the meter and kilograms. And after that, 1889, the first conference on weight and measure approved a system of measure with the base unit meters, kilogram, and second. And is continued to 1954, ampere, Kelvin, candela are officially adopted as base units by 10 CGPM. So this is the evolution of the SI units, everyone. And you also can see the timeline of the history of the international system of units since John Wilkins' 1668 essay is called To a Meter Bar. And photograph shows a marble meters, a standard in Paris, dating from the 18th century until 2018. In 2018, the new SI will specify the exact values of 7 fundamental constants. We will talk about the 7 fundamental constants in the next slide. And then from this, 1960, The 11 CGPM adopts the name International of System of Units, or we can say SI units, with the base units meter, kilogram, second, ampere, Kelvin, and candela. And the meter is redefined as the wavelength of radiation from a specific excitation in krypton 86, not from the previous or not from the Jones-Wilkins assay. In 1983, a new definition of the meter links it to the speed of the light in vacuum. So, how to make a system of units? A system of units to express all physical quantities or all physical measurement must take into consideration all physical quantities and the equation that relate those quantities, namely law of physics. I'll give you the example. F equals to mass times A, or mass times dV over dt, or mass times d square x over dt square, where force is F, mass is m, acceleration is A, velocity is v, length is x, time t, or all quantities, and the relations are Newton's second law of motion and the basic dynamics. Now here, we have to be careful to choose a subset of independent base quantities. Allows one to derive the remaining quantities as a function of the chosen subset through the accepted laws of physics. So the selection of the base quantities is not unique, but they must be complete and non-redundant. For example, in our formula, from the equation, we know about 6 quantities and 3 constraints from this formula. Which one is the 6 quantities? Force, mass, acceleration, velocity, length, and time. Now, choosing either force or mass and any 2 of the remaining 5 quantities would give us an independent set of 3 base quantities. So that is why we also can try to find the derived quantities from the base quantities. We only choose either force or mass and any 2 of the remaining 5 quantities as the independent set of 3 base quantities. So we must assign the specific reference quantity to each base quantity. So the reference quantity can be a specific artifact, as is the case for the base quantity of mass in the present in international units. We also can use different examples to define the other equivalent relation from the first example or equation to another example equation. I think that's very, very important. Now, there are 7 base quantities in the present: time, length, mass, electric current, thermodynamic temperature, amount of substance, and then the luminous intensity. And then in the table, you also can see the symbol for the quantity one by one, and name of SI units for each base physical quantity, and also the symbol for SI units. For base physical quantities length, the symbol is L, name of SI units is in meters, and then the symbol for SI unit is M. Base physical quantities for mass, and its symbol is M. The name of SI unit is in kilogram, and the symbol for SI unit is in kg. Time, the symbol for time is T, name of SI unit is in second, and the symbol for SI unit is S. Electric current, its symbol is I, name of SI unit is ampere, and then its SI unit symbol is A. Thermodynamic temperature, its symbol is uppercase T, the SI unit's name is Kelvin, and then SI unit symbol is K. Amount of substance, its symbol is M, name unit's name, mole, SI unit's name is mole, and then SI unit symbol is MOL or mole. Luminous intensity, its symbol is I, and then SI unit's name is candela, and the symbol for SI units is CD. Now, from the definition of base physical quantities, based on the history of the base quantities, the unit of length or meters. So we can define one unit of length is the meters is the length of the path traveled by light in vacuum during a time interval 1/299,792,458 of a second. So this is a new definition from John Wilkins. Unit of mass, its unit is kilogram. The kilogram is the unit of mass. It is equal to the mass of the international prototype of the kilogram. Unit of time, its unit is in seconds. So the second is the duration of 9,192,691,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground of the cesium-133 atoms. Unit of the electric currents or ampere. So the ampere is that constant current which is maintained in the two straight parallel conductors of infinite length, of negligible circular cross-section and placed 1 meters apart in a vacuum, would produce between these conductors a force equal to 2 times 10 to the power -7 newtons per meter of length. Unit of thermodynamic temperature, which is Kelvin. So the Kelvin unit of the thermodynamic temperature is the fraction of 1/273.16 of the thermodynamic temperature of the 3 points of the water. Unit of amount of substance, mole. The mole is the amount of substance of a system which contains as many elementary entities as there are atoms in 0.0112 kilograms of carbon-12. So its symbol is mole. And then the second definition is when the mole is used, the elementary entities must be specified and may be atoms, molecules, ions, electrons, or other particles or specified groups of such particles. The unit of luminous intensity is candela. The candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 times 10 to the power of 12 hertz, and that has a radiant intensity in that direction of 1 over 683 watt per stray radian. And after that, from the development of the fundamental base quantities, and there are some new SI will also as a base quantities, which is frequency, velocity, action, electric charge, heat capacity, amount of substance, and luminous intensity. So the new base quantities are the frequency, the velocity, action, electric charge, heat capacity, amount of substance, and luminous intensity. And this is the present SI-based quantities. Talking about derived quantities, we know there are new 7 base quantities and present SI base quantities. So the all other units that are obtained or derived from the fundamental units are called derived units. Derived units are not independent. They are basically composed of 2 or more fundamental units. I'll give you the example. So there are some derived quantities in the table. Displacement, area, volume, speed, velocity, acceleration, force, energy, density, moment, power, work, momentum, and pressure. And this is the symbol for derived quantities. And the SI unit is in meters. SI unit is in meters square for area. SI units of volume is meter cube, speed meter per second, and so on. And this is the symbol for the derived units. So what is the similarities between fundamental units and derived units? So the first similarity is both fundamental units and derived units are part of international system of units or SI units and are standardized. And the second similarity, both fundamental units and derived units are overwhelmingly used in common purpose to express corresponding physical quantities. Now, the question is the difference between the fundamental and derived units, everyone. Friends, the difference between fundamental units and derived units is number 1, fundamental units are all those units which are independent of any other units, but that is different from derived units. Derived units are all those units which are obtained by multiplying and or dividing one or more fundamental units with or without introducing any other numerical vectors. And the second difference is fundamental units cannot be further reduced to elementary level. In fact, these are elementary units. Different from derived units can be reduced to its elementary level, which are composed of fundamental units. The third difference is fundamental units cannot be expressed in terms of derived units, but derived units can be expressed in terms of fundamental units. Fourth, only 7 fundamental units exist in matrix system or SI system. Derived units, there exists a large number of derived units in matrix system. And the fifth, 7 fundamental units are meter, kilogram, second, Kelvin, mole, ampere, and candela. And then few derived units are Newton, joules, watt, volt, Pascal, Celsius, and so on. So there are 5 difference between fundamental and derived units. And thank you so much, everyone. So that is about the basic fundamental units and derived units, and also the history of fundamental units. In the second video, I will show you the example of fundamentals and derived units. And thank you so much, everyone. And see you for the second video.